What if I told you that a single Belgian engineer invented a suspension system so advanced that it made a French family car handle better than sports cars while riding smoother than a Rolls-Royce? This is the story of Paul Magès, the man who revolutionized automotive suspension with a technology so radical that American manufacturers called it impossible. Picture this. It's 1955 at the Paris Auto Show, and journalists are watching a Citroën DS demonstration. The car is loaded with 4 passengers and luggage. As weight is added, something extraordinary happens. Nothing. The car doesn't squat, it doesn't lean, it maintains perfect ride height automatically. Then the driver accelerates hard around a corner. The car stays completely flat, defying every law of automotive physics known at the time. One British journalist wrote that watching it was like witnessing magic. This wasn't magic. It was the result of Paul Magès' hydropneumatic suspension system, a technology that would dominate luxury car engineering for the next half-century and spawn every modern air suspension system we see today. While Detroit's Big Three were pouring millions into bigger engines and chrome bumpers, a soft-spoken Belgian engineer in Paris was quietly solving one of automotive engineering's greatest challenges: how to combine comfort with performance without compromise. To understand why Magès' invention was revolutionary, we need to travel back to the early 1950s. The automotive world was experiencing its golden age. Post-war prosperity meant consumers wanted more than basic transportation. They wanted comfort, style, and performance. But there was a fundamental problem that every manufacturer faced. Suspension design was always a compromise. Conventional steel spring suspension hadn't changed much since the 1930s. You had coil springs or leaf springs, shock absorbers, and that was basically it. If you wanted a comfortable ride, you used soft springs. But soft springs meant the car would lean dramatically in corners, dive under braking, and squat during acceleration. Body roll could exceed 15 degrees in hard cornering. If you wanted better handling, you stiffened the springs. But stiff springs meant every bump transmitted directly to passengers. Your kidneys would hate you after an hour on rough roads. Mercedes-Benz was producing some of the world's finest luxury cars, but even their best engineers couldn't solve this fundamental trade-off. General Motors had the resources to tackle any engineering challenge, yet their solution was simply to make cars bigger and heavier, using mass to dampen road imperfections. It was crude, but effective enough for American highways. In France, Citroën had different ideas. The company had always been unconventional, dating back to founder André Citroën's obsession with advanced engineering. By 1954, they were developing their next flagship model, internally designated Project D. This car needed to showcase French engineering supremacy. It needed to be unlike anything else on the road. Enter Paul Magès. Born in 1908, Magès wasn't your typical automotive engineer. He'd started his career in hydraulics, working on industrial equipment. When he joined Citroën in 1945, he brought a completely different perspective to automotive problems. While other engineers thought in terms of springs and dampers, Magès thought in terms of fluid dynamics and pressure differentials. The problem Citroën presented to Magès was straightforward, but seemingly impossible. They wanted a suspension system that could maintain constant ride height regardless of passenger or cargo load. A car that wouldn't nosedive under hard braking or squat under acceleration. A car that could corner flat while still providing boulevard ride quality. Every other manufacturer had tried and failed to achieve even 2 of these goals simultaneously. Citroën wanted all of them. Magès' solution was radical. Instead of using steel springs to support the car's weight, why not use hydraulic pressure? The concept was elegantly simple. Each wheel would have a hydraulic cylinder. These cylinders would be connected to a central high-pressure pump. As the car's load changed, the system would automatically adjust pressure to maintain ride height. But here's where Magès' genius really showed. A purely hydraulic system would be incredibly harsh. Hydraulic fluid is incompressible. Hit a bump, and the shock would transmit directly through the system like hitting concrete. Magès needed something that could compress and expand to absorb road impacts. His solution? Nitrogen gas. The heart of Magès' system was the spherical accumulator. Picture a metal sphere about the size of a grapefruit, divided internally by a flexible diaphragm. On one side, high-pressure nitrogen gas. On the other, hydraulic fluid. When the wheel hit a bump, hydraulic fluid would rush into the sphere, compressing the nitrogen. The gas would act like a progressive spring. The more it compressed, the harder it pushed back. But unlike a steel spring with linear characteristics, the gas provided a progressive rate that got stiffer under extreme loads. The mathematics were beautiful. Nitrogen follows Boyle's law. Pressure times volume equals a constant. As volume decreased, pressure increased exponentially. This meant the suspension would be soft and compliant over small bumps, but would naturally stiffen to prevent bottoming out over large impacts. No steel spring could replicate this progressive characteristic, but the real innovation was the height control system. Magès designed a mechanical height sensor for each wheel, essentially a lever connected to a valve. If the car's body dropped below the predetermined height, the valve would open, allowing high-pressure fluid to flow into that wheel cylinder, raising the car. Too high? The valve would release fluid back to the reservoir. The response time was under 2 seconds. The system operated at extraordinary pressures, up to 2,500 psi, or 175 bar. For context, a typical car tire operates at 32 psi. This extreme pressure meant components had to be manufactured to aerospace tolerances. A single leak would be catastrophic. Citroën had to develop entirely new manufacturing processes, new seals, new metallurgy. The hydraulic pump alone required precision that exceeded anything in automotive production at the time. Testing began in 1954. The first prototypes were disasters. Seals burst. Lines ruptured. The system would work perfectly for a few hours, then fail spectacularly, dropping the car onto its bump stops. Citroën executives were nervous. Project D was consuming massive resources. Some board members pushed to abandon Magès' system and return to conventional suspension. But André Lefebvre, Project D's chief engineer, believed in Magès' vision. He gave him more time, more resources. Magès and his team worked 18-hour days, systematically solving each failure point. They developed new seal materials that could withstand the pressure and temperature variations. They redesigned the hydraulic pump 7 times before achieving acceptable reliability. By early 1955, they had a working system, but working wasn't enough. It had to be perfect. Citroën's reputation would ride on this technology. They subjected prototypes to torture tests that exceeded anything a customer would experience. Cars ran continuously for weeks at maximum load over Belgian cobblestones, some of Europe's roughest roads. They tested in the Sahara Desert's heat and Scandinavia's Arctic cold. The results were extraordinary. The hydropneumatic suspension provided ride quality that matched or exceeded Rolls-Royce, the gold standard of luxury. But unlike a Rolls, which wallowed through corners like a yacht in heavy seas, the Citroën stayed flat. Body roll was reduced by 70% compared to conventional suspension. Brake dive and acceleration squat were virtually eliminated. But here's where it gets really interesting. The system offered capabilities no conventional suspension could match. Need to change a tire? Push a lever, and the car would rise 6 inches, making jack unnecessary. Driving through a flooded road? Raise the suspension to maximum height for extra clearance. Want sporty handling? Lower it for a lower center of gravity. One car, multiple personalities, all controlled hydraulically. The suspension could even compensate for uneven loads. Load heavy cargo on one side, the system would automatically level the car within seconds. Lose a wheel? The remaining 3 hydraulic cylinders could support the car's weight, allowing the driver to limp to safety. This wasn't just suspension, it was an active chassis management system decades before electronics made such systems common. When the Citroën DS debuted at the 1955 Paris Auto Show, it caused a sensation. The car looked like it had arrived from another planet, aerodynamic, futuristic, with a drag coefficient of 0.36 when most cars were above 0.50. But it was the suspension demonstration that truly stunned observers. Citroën's demonstrators would load the car with passengers, then remove them. The car would maintain perfect stance throughout. They'd disconnect the rear hydraulic spheres while driving. The car would continue normally on just the front suspension. They'd drive the car on 3 wheels. Most dramatically, they'd have someone stand on the rear bumper, then step off. The car would immediately self-level without any bounce or oscillation. Orders flooded in. On the first day alone, Citroën received 12,000 orders, more than most manufacturers sold in a month. By week's end, they had 80,000 orders. The motoring press was unanimous in its praise. British magazine Autocar called it the most significant automotive advance since the self-starter. Road and Track declared it the car of the future, available today. But not everyone was convinced. Detroit's reaction was skepticism, bordering on dismissal. General Motors engineers publicly questioned the system's reliability and cost. Ford executives called it unnecessarily complex. Chrysler's chief engineer was quoted saying, "Americans want simple, reliable transportation, not science experiments." The real reason for American resistance was more complex. Implementing hydropneumatic suspension would require massive retooling. It would obsolete billions of dollars in spring and shock absorber manufacturing infrastructure. It would require retraining entire workforces. And most importantly, it would require admitting that a small French company had out-engineered the mighty American auto industry. There were legitimate concerns. The system was expensive, adding roughly 15% to manufacturing costs. It required specialized maintenance. The hydraulic fluid was hygroscopic, meaning it absorbed moisture from air, requiring periodic changes. Early systems could be temperamental, occasionally dropping a corner if a sphere's diaphragm failed. But these were solvable problems, not fundamental flaws. Meanwhile, Magès continued refining his invention. In 1957, he developed an improved height corrector that responded even faster. In 1959, he created a load-sensing brake valve that automatically adjusted brake pressure based on vehicle load, preventing rear wheel lockup when the car was lightly loaded. This was essentially a mechanical anti-lock brake system 2 decades before electronics made ABS common. The second-generation system, introduced in 1965, was even more sophisticated. It featured dual-circuit hydraulics for redundancy. If one circuit failed, the other could maintain basic suspension function. The spheres were redesigned with improved diaphragms that lasted longer. Operating pressure was optimized for better efficiency. By 1967, Citroën introduced Derivi, power steering integrated into the hydropneumatic system. This wasn't ordinary power, steering. The hydraulic pressure provided speed-sensitive assistance, more help at low speeds for parking, less at high speeds for better feel. The steering was self-centering, using hydraulic pressure to return the wheels to straight ahead. It was the first speed-sensitive power steering system in production. The technical specifications were remarkable even by modern standards. The system could cycle through its full suspension travel 5 times per second. Response time to road inputs was under 5 milliseconds. The hydraulic pump, driven by the engine, could generate 2,500 psi continuously while consuming just 3 horsepower. The entire system weighed only 65 pounds more than conventional suspension. Remarkable, considering it included power steering and self-leveling capabilities. Rolls-Royce took notice. In 1965, after extensive testing, they licensed Magès's technology for the Silver Shadow. This was the ultimate validation, the world's most prestigious luxury car manufacturer admitting that hydropneumatic suspension was superior to their traditional setup. The Silver Shadow's ride quality became legendary, with journalists describing it as floating on a cloud. Mercedes-Benz followed suit with their experimental C111 and later the 450-cell 6.9. Maserati used it on the Quattroporte too. Even conservative BMW experimented with hydropneumatic suspension, though they never put it into production. The technology was spreading slowly but surely. But the most impressive implementation came with the 1970 Citroën SM. This was Magès suspension paired with a Maserati V6 engine. The combination was intoxicating. Supercar performance with limousine comfort. The SM could cruise at 140 mph while providing a ride quality that let passengers read a newspaper. It could corner at speeds that would have conventional cars on their door handles, yet never transmitted harsh impacts to occupants. The SM featured another Magès innovation, variable ride height based on speed. Above 65 mph, the suspension would automatically lower the car by 15 mm, reducing aerodynamic drag and improving stability. Below 30 mph, it would return to normal height for better ground clearance. This was active aerodynamics before the term existed. The system's most impressive demonstration came during emergency maneuvers. Under maximum braking from 60 mph, a conventional car's nose would dive 4 to 6 inches. The Citroën's nose would drop less than an inch. This meant weight transfer to the front wheels was minimized, keeping more weight on the rear wheels for better braking stability. Stopping distances were reduced by up to 15% compared to conventional cars of similar weight. Cornering was equally impressive. A conventional sedan might achieve 0.75 g lateral acceleration before losing grip. The hydropneumatic Citroëns could exceed 0.85 g while maintaining comfort. The suspension would actually firm up during cornering as hydraulic pressure increased on the outside wheels, providing progressive resistance to body roll. It was like having adaptive dampers decades before electronic control made them possible. Yet despite its clear technical superiority, hydropneumatic suspension remained a niche technology. Why? Cost was certainly a factor. The system required expensive materials and precise manufacturing. But the real barrier was psychological. The automotive industry was conservative. Manufacturers had billions invested in conventional suspension. Dealers were trained to service springs and shocks, not hydraulic systems. Customers were wary of complexity. American manufacturers conducted their own tests. General Motors built several prototypes with hydropneumatic suspension in the early 1960s. The results were impressive. Ride quality improved 40%, handling improved 25%, and brake dive was virtually eliminated. But the bean counters killed it. The system would add $400 to the cost of each car, about $3,500 in today's money. For a mass-market manufacturer selling millions of units, that was unacceptable. There were also maintenance concerns. While the system was reliable when properly maintained, it required specific expertise. The hydraulic fluid needed changing every 30,000 miles. The sphere's diaphragms would eventually wear out, requiring replacement every 60,000 to 80,000 miles. For Citroën dealers trained in the system, this was routine. For a typical American mechanic used to replacing shock absorbers, it was alien technology. The 1973 oil crisis changed everything. Suddenly, fuel economy mattered more than comfort. Hydropneumatic suspensions added weight and parasitic pump losses, about 1 to 2 mpg, became a liability. Manufacturers focused on making cars lighter and more efficient. Complex hydraulic systems didn't fit that paradigm, but Magès' influence extended far beyond hydropneumatic suspension itself. His work proved that active suspension was possible, that a car's dynamics could be controlled in real time. This inspired a generation of engineers to think differently about chassis design. In the 1980s, Lotus developed active suspension for Formula One using principles Magès had pioneered. Instead of mechanical height sensors, they used electronic sensors. Instead of hydraulic pressure alone, they used computer-controlled actuators. But the fundamental concept, using hydraulics to control suspension geometry, came directly from Magès's work. Modern air suspension systems are direct descendants of hydropneumatic suspension, replace hydraulic fluid with air, nitrogen spheres with air springs, and you have the system used on today's luxury cars. Range Rover, Mercedes S-Class, Audi A8, they all use air suspension that operates on principles Magès established. The height sensors, the automatic leveling, the variable spring rates, it's all there, just with different technology. Even more advanced systems like Mercedes' active body control and Audi's predictive suspension use hydraulics exactly as Magès envisioned. They've added electronics and computer control, but the fundamental architecture, hydraulic cylinders controlling suspension movement, remains unchanged. These systems can scan the road ahead and adjust suspension before hitting bumps, achieving ride quality Magès could only dream of. The most telling validation came in 2017 when Citroën introduced progressive hydraulic cushions, essentially a simplified version of Magès' original concept. After abandoning hydropneumatic suspension in 2017 due to cost, they realized they needed its benefits to remain competitive. The new system uses hydraulic bump stops that provide the progressive damping Magès achieved with gas spheres. It's simpler and cheaper, but it's still fundamentally his idea. Consider the modern McLaren. Their proactive chassis control uses interconnected hydraulic dampers to eliminate body roll without anti-roll bars. The hydraulic fluid transfers between dampers based on cornering loads, exactly like Magès's system transferred fluid between cylinders. McLaren's engineers freely admit they studied Citroën's patents when developing their system. Paul Magès retired in 1973, having spent nearly 30 years perfecting his suspension system. He held over 100 patents related to hydraulic suspension and vehicle dynamics. He passed away in 1981, just as the automotive world was beginning to embrace electronic control systems that would finally make his vision of adaptive suspension mainstream. His legacy is everywhere in modern automotive engineering. Every car with air suspension, every vehicle with adaptive dampers, every system that maintains ride height automatically, they all trace their DNA back to Magès's workshop at Citroën. He proved that hydraulics could do more than just provide power assistance. They could fundamentally transform how a vehicle behaves. The numbers tell the story. Citroën produced over 9 million vehicles with hydropneumatic suspension between 1955 and 2017. Rolls-Royce used it for 15 years. Mercedes-Benz spent over $500 million developing their active body control system based on Magès principles. Today's luxury car market, worth over $500 billion annually, relies heavily on suspension technologies he pioneered. But perhaps Magès's greatest achievement wasn't technical, it was philosophical. He showed that engineering conventions exist to be challenged, that complex problems sometimes require complex solutions, that a small team with a radical idea could out-engineer the world's largest corporations. In an era of corporate groupthink and risk aversion, Magès stood as proof that individual genius still mattered. The Citroën DS remains one of the most influential cars ever built. It's in the permanent collection at the Museum of Modern Art. It was voted the most beautiful car of all time by Classic and Sports Car magazine. But its real beauty was invisible, hidden in hydraulic lines and nitrogen spheres, in pressure valves and height correctors. It was the beauty of engineering perfection, of solving an impossible problem with elegant physics. Today, when you see a Range Rover maintaining perfect composure over rough terrain, or a Mercedes S-Class gliding over potholed roads, or a McLaren cornering flat at impossible speeds, you're witnessing Paul Magès's vision. He didn't just outsmart Citroën with a secret hydraulic system. He outsmarted an entire industry that said his ideas were too complex, too expensive, too radical. The automotive industry eventually learned what Magès knew all along, that comfort and performance aren't mutually exclusive, that complexity in service of perfection is worthwhile, that hydraulics could indeed revolutionize vehicle dynamics. It just took them 60 years to catch up. Modern engineers, armed with computer simulations and electronic controls, still struggle to match what Magès achieved with purely mechanical systems. His hydropneumatic suspension remains a masterclass in engineering elegance, complex enough to solve the problem, simple enough to manufacture, reliable enough to last decades. The irony is delicious. American manufacturers dismissed Magès's invention as unnecessarily complex while spending billions developing inferior alternatives. They called it a science experiment while it was winning rallies and setting speed records. They said customers wouldn't pay for it while Rolls-Royce was licensing it for their most expensive models. In the end, Paul Magès didn't just design a suspension system. He designed the future. Every modern advancement in chassis control, from electromagnetic dampers to predictive suspension, builds on foundations he laid. He proved that one engineer with vision could change an entire industry. That's the real secret of his hydraulic system. Not how it worked, but what it represented. The triumph of innovation over convention, the victory of engineering excellence over corporate conservatism, the power of solving problems everyone else said couldn't be solved. What revolutionary technology is being dismissed today as too complex or expensive? What modern-day Paul Magès is working in obscurity on the next breakthrough? That's the question worth asking, because if history teaches us anything, it's that the next revolution in automotive technology probably won't come from where we expect. It'll come from someone willing to challenge everything we think we know. If you enjoyed this deep dive into engineering history, make sure to subscribe for more stories of innovations that changed the automotive world. And let me know in the comments, what forgotten automotive technology do you think deserved more recognition? Until next time, keep questioning the conventional wisdom.